Welcome to this video on orbitals. And if you've come to this video without having watched it before or without knowing what an orbital is, you probably have this question. Where around the nucleus do electrons spend their time? If you've watched the video on the Bohr model, you know that electrons certainly don't orbit the nucleus like Bohr thought they did. And we said that this model was incorrect. And so you have this question, where do they spend their time if the Bohr model isn't correct? Well, the answer I'm going to give you is probably incredibly unsatisfying. And that answer is we cannot know with 100% certainty. We will never know where exactly electrons spend their time around the nucleus. What we can do is describe where electrons are likely to be at any given time using what are called probability density distributions. And this sounds like really advanced college level stuff, and it really is, but we can look at it with a fairly simple framework to understand what it's saying. Probability, that just refers to, you know what probability is, but in this case it refers to the chance of finding an electron at any given point around the nucleus. And we relate probability with density in this diagram. What does that mean? Well, we have all these dots. This red thing here is obviously the nucleus, the center of the atom. And these dots, when we have areas of high density, so really close around the nucleus, this just indicates, I'm going to get a darker color because you can't really see that. This just indicates a high probability of finding an electron. High probability of finding an electron. That symbol just means an electron. What about out here, where the density is lower? Out here. So farther away from the nucleus, in this case, probably a hydrogen atom. Over here, because the density is lower, there's a low probability of finding an electron that far from the nucleus. So a high density indicates a high probability of finding an electron, and a low density indicates a low probability. And the distribution is just this diagram right here. It's a pictorial representation of where we're most likely to find electrons. Unfortunately, we can never say the electron is right here. We can say, oh, there's an 86.9% chance that it's going to be there. So we can only describe the position of electrons around a nucleus in terms of probabilities. And the reason that is, it's a very complicated quantum mechanical, some quantum mechanical ideas are involved with it, but I guarantee if you move forward, you will study this idea at college. But we can actually move further just in high school, and we can sort of look at the probability this probability density distribution as a graph. So over here, we've got on the x-axis distance from nucleus. So as we move to the right, we move farther and farther away from the nucleus. And here we've got something that's called radial probability, and that's sort of what we did here. It just means the probability of finding an electron a certain distance from the nucleus, so on a certain ring, if you will, if you think about it in terms of the Bohr model. And if we graph the probability density distribution for hydrogen, for the one electron in hydrogen, it's going to look something like this. It's going to be low, it's going to go up like this, it's going to crest, and then it's going to come down and get pretty close to the x-axis. If we take the area underneath this graph, this is going to indicate the probability of finding an electron within that distance to the nucleus. Now, it looks like most of the area underneath this graph is kind of to the left of this point, right, of this x value. And we can in fact say that we can conjecture that maybe this much of the graph represents 90% of the probability. So an electron is 90% likely to be no farther than this arbitrary value, let's call it, I don't know, Q, from the nucleus. And this 90% value is important because we can define the area, the region around a hydrogen atom, which encloses 90% of its electron probability. So maybe over here we could say, if I take a red, maybe this is 90% of the probability distribution. So there's a 90% chance that the electron is somewhere in there. And again, that just relates to the area underneath this graph. We call this region, and this is really important, the 1s orbital. And so the orbital is a three-dimensional object, looks like this, which represents a probability density distribution. So over here, this is sort of the same thing we looked at before. This is the probability density distribution for hydrogen, and this ring represents 90% of the probability of the electron density probability. So there's a 90% chance that the hydrogen's electron is hanging out this close from the nucleus. So this is just the probability distribution, which we looked at before. Probability distribution. We're using big fancy words now. You should be proud of yourself. And over here, this is an orbital. This is the three-dimensional surface. Three-dimensional surface, because remember, the atom takes up three-dimensional space. The electron could be sort of behind the nucleus, it could be in front of the nucleus. This is the 3D surface which encompasses 90% of that electron density probability. And this is how we describe where electrons spend most of their time. So if we go back to our original question, where around the nucleus do electrons spend their time, we approximate that electrons exist within orbitals, because there's a 90% chance that an electron, hydrogen's electron, exists within that orbital. But of course, there are more elements than just hydrogen, and so we have different kinds of orbitals to describe different kinds of electrons, if you will, or electrons in different kinds of elements. The s orbital, so remember this orbital which we looked at for hydrogen was an s orbital, it was the 1s orbital. S orbitals always look like spheres. And so sometimes some electrons will inhabit s orbitals, and they'll live within an orbital which is a sphere. But not all orbitals are spherical. We can have orbitals which look very different, and those orbitals are called p orbitals, and these are dumbbell-shaped. And we will not discuss why they're dumbbell-shaped, you just need to know that they are. And so why don't we sketch in three-dimensional space what these orbitals look like. And so this 1s hydrogen orbital looks something like this. If the center of those axes is the nucleus, the origin is the nucleus, this sphere represents the 1s orbital. The 2p orbital, which again we'll look at in the next video, the specific p orbitals, but the 2p orbital, or just a generic p orbital, would look like this. It would have one part extending in the y direction, which looks like that, one part extending in the z direction, looking like that, so that's coming out at us, and one part extending in the x direction. So it has 6 sort of arms altogether. And this is really complicated. This looks really, really complicated, and you might be saying, James, I am losing you. But don't. You shouldn't say that, because this is not a very complicated topic, or it's not anywhere more complicated than this idea. These p orbitals are just three-dimensional surfaces which represent the likelihood of finding little electrons within these orbitals. So we're going to say that there's a 90% chance that an individual electron is going to hang out in this orbital if we know it inhabits a p orbital. So there's a 90% chance that all the electrons within this atom, for which these orbitals describe, are going to hang out somewhere in one of these orbitals. And a much better drawing of the p orbital is like this, and so this is the p orbital extending in the x direction, this is the p orbital extending in the y direction, this in the z direction, and this is what one complete p orbital looks like. And again, these are just three-dimensional surfaces which describe where electrons hang out. So electrons are probably moving around in here, moving around in here like that, and over here in this picture There are a bunch of electrons. There are 2 in each orbital, most likely, if the subshell is filled, like that. And again, we may even find an electron maybe here. Maybe even like over here. There's a 10% chance that electrons do not inhabit the orbitals which describe them. Orbitals, this is a big idea, orbitals are just approximations. They're approximations of where electrons hang out. And they can get really super complicated. We can move beyond the p level, and the elements in the transition metal sequence of the periodic table have electrons in d orbitals, which look like this. They're these kind of weird, complicated shapes that extend in different directions. But the idea is always the same. There's a 90% chance that electrons reside in these orbitals. And the farther out you go with these orbitals, the higher energy electrons you have. So maybe your d orbital extends farther like that. Maybe this is a higher level d orbital. Electrons that are over here are going to have more energy than electrons in a lower orbital. And there are even more orbitals, something called we talked about d orbitals, something called f orbitals, and these describe the location of electrons in lanthanides and actinides. And these are the complicated elements at the bottom of the periodic table, and we're not even going to show them because they're so complicated. But again, the main idea you should take from this video, if you remember nothing else, is this concept right here. The idea that an orbital is a three-dimensional surface which represents 90% of the probability distribution of an electron or electrons, and the probability distribution just describes the likelihood of finding an electron at a specific distance from the nucleus. That's what this graph represents here. That's what this representation represents here. It's all about the probability of finding electrons around a nucleus. And how do we do that? Back to our initial question, we use, went too high. We use orbitals, which are the subject of this video. And if you'd like to see how we specifically define where electrons hang out, which specific orbitals they inhabit, I encourage you to watch the video on electron distributions. I'll see you there.